Point estimates are sharp but almost never on point. Intervals add context. The interval says, "We're this much confident the true mean lives in this neighborhood." They are also more believable. Compare these two statements. 1. Each portion of this meal has 350 calories. 2. Each portion of this meal has 350 calories. Give or take 5. Which one was more believable? Every time you take a new random sample, you have a new sample mean. So the sample mean is itself a random variable with a certain probability density function. Central limit theorem says if your sample size is large, this probability density function is Gaussian. We can now understand how x bar behaves and draw conclusions about it. This is the recipe for a confidence interval. Note that the uppercase x bar is a random variable. In practice, we only have a single observed value from this random variable calculated from our one and only sample. We replace x bar with this single observed value and we now have a confidence interval. Margin of error determines the length of your confidence interval. Want a tighter interval? Grow n, accept a lower confidence, or reduce the noise. No magic, just math. A large sample size lets us plug in S for sigma. We can be 95% confident that the true mean is between 70.25 and 75.35 beats per minute. You can be as confident as you like, but you need to pay for it by being more cautious. That is to say, you would need a wider net. However, make sure your net is not too wide or you may risk sounding ridiculous. Imagine if a researcher says, "We are 100% confident that the resting heart rate of adult humans is between 0 and 1000. Well, that's very confident and totally useless. The interval moves from sample to sample. The mean doesn't. The confidence level is about the long-run success rate of this method, not the probability of this one interval successfully capturing the true mean. Smaller margin needs bigger sample size. For example, double precision means 4 times larger sample.